full of CS majors trying to figure out Slang clicker.
How many CS majors does it take to figure out?
Okay, anyway, here's the meeting flag. Some background. If you see undercover jump table in Ghidra, you should be sad. That's not good. So I'll give everyone a few seconds to type the meeting flag.
That's why you need volatile.
Volatile?
Yes.
V tables?
What?
V tables?
No, I mean with volatile, every store and load instruction will be treated as is. Not in my compiler.
All right, so anyway, let's continue. So it's a show of hands, how many of you have Ghidra installed? Because we're gonna do like a live walkthrough later, and I think it's gonna be a lot more fun if you have Ghidra. So if you don't, there's a link here. You can get started with downloading it. Highly recommend that you do that. It's like a bit of a pain because you need Java first. If you don't have Java, you need to install Java and then install Ghidra.
Oh, no.
But yeah, so if you don't, then make sure you get started with that.
Funny thing, that link doesn't exist, but our intro slides do cover how to install Ghidra, like from the beginning of the semester. So go to like our meetings tab and then go there. Yes.
Yeah, and so before we get started with like the actual meeting content, just a quick note about joining the club and being a helper. So FA20 is kind of interesting in the sense that we don't really have any like formal application process to become a helper or an admin or anything like that. It's essentially you get invited to become helper, exec, or whatever based on your contributions to the club and kind of what would make you stand out in some sense. It's attending meetings, talking to other people at meetings, doing Pony CTF, engaging with content challenges, and sort of kind of liking the philosophy of the club, which is we like to teach each other stuff that we know. We sort of have a learning mindset. We always want to learn new things. We want to learn from other people, from meetings, but then also just from talking to other people in the club. And we always want to make the club better. So if you're interested in that and you sort of are able to demonstrate that interest, then being helper admin would be perfect for you. And if you do have an interest in kind of getting more involved with the club, then definitely send an admin like a DM on Discord or like talk to them in person. Express interest just in the Discord channels or whatever. And there's a link here for some more information on that. So with that, we will get to the actual meeting content. This meeting is going to be about reverse engineering x86 binaries. So just some review from last meeting about what reverse engineering is. At the simplest level, reverse engineering is figuring out how something works. We are mostly going to look at software. You can, reverse engineer hardware. You can reverse engineer like mechanical assemblies or things like that. Our focus, since we are like mostly a cybersecurity club, is just going to be reverse engineering pieces of code. So really your goal when you're reverse engineering is to figure out how a piece of code works, or more generally get something useful out of a piece of code. Maybe not understand completely how it works, maybe understand something about it. Essentially get some information out of a piece of code. Why is reverse engineering useful? Why do we do it? Well, I guess the flippant answer would be to solve CTF challenges. But also beyond that, in the real world, when you're trying to find vulnerabilities in software, often the first step will be to reverse engineer it, especially if you don't have like source code, things like that. Reverse engineering, kind of in my opinion, also makes you better at programming, because like one of the skill sets you need in programming when you're looking at somebody else's like uncommented 1,000 line piece of code is you need to figure out how it works. And sort of having experience reverse engineering in kind of more of a security context really does make you kind of better at that. And there's so much more you can do with reverse engineering. You know, you can do like formal verification of software, there's all kinds of cool stuff. There's sort of two extremes in terms of reverse engineering techniques that we're going to look at today. One is static analysis, which is essentially analyzing a piece of code without running, so just looking at the code. And then there's dynamic analysis, which tries to analyze a piece of code while running it. But these aren't like necessarily two distinct things that you always have to do one or the other. There's some kind of overlap between them, and typically you would do a combination of the two, maybe even at the same time. And since we are going to do x86 reverse engineering, we are going to stare at a lot of assembly. So just some review on assembly from Sam and Emma's really wonderful slides from Sunday. So what is assembly? Assembly is essentially like a human readable version of machine code. So computers, CPUs operate on ones and zeros, and assembly is uses mnemonics and human readable names for registers and things like that to give you some more easily understandable version of what computer is executing. But it's still very, very low level. I mean, it's just one level above machine code, really. So here's an example of a C function, and the x86 assembly translates to. So like the green instructions that you see in the beginning are what's called the function prologue, so it like sets up the stack and stuff. You have some local variables, and then you have a return, some up in addition and then a return. And typically in an executing program, you're going to have instruction memory, which stores the code that the program is executing. You will have registers that essentially store the state of the CPU. And you have, of course, kind of your RAM memory, and part of that is the stack, which stores local variables and essentially handles functions. So before we move on, any questions so far about kind of any of the background material, assembly, general engineering, anything? No? All right. So what is this meeting about? So last Thursday, Juniper talked about reverse engineering interpreter code, so Python mainly. Today we are going to talk about reverse engineering binaries, so compiled programs, compiled executables. The fun or not so fun thing, depending on how you look at it, is going to be you're going to have a lot less information to work with. When you're reverse engineering a piece of Python code or maybe like JavaScript code, you typically have human readable source code. Like Python, maybe it's like obfuscated in some way. There's like funny variable names, but at least it's like somewhat human readable. A binary is literally just ones and zeros, because that's what executes on your machine. So what is there in this binary? Well, there's of course the machine code. There's the instructions that the CPU needs to execute to run your program. Sometimes you will have like some information from the source program, maybe function names, variable names, things like that. But in a reverse engineering context, you probably won't, because, well, it's harder without them. And kind of the bare minimum, like key idea here is that really all that is going to be there in a binary is pretty much what's needed to execute that program. You won't have really anything more than that, or you don't need to at least. And we're kind of going to work with like a running example. I want to make this sort of like a workshop in some sense. So this is one of the meeting challenges from today. I'll give everybody like a couple of minutes to get this downloaded. What we're going to do is, using the stuff we learned in this meeting, we're going to be able to solve this challenge by the end. And if you're able to follow along, it's going to be a lot of fun. So yeah, just I'll give everybody a minute or so to download this. If anybody's having any trouble getting it downloaded, you can let me know. So it should be on the on like ctf.sigpwny.com under reverse engineering too. Right, does everybody have it? Any trouble? Yeah?
What exactly do we need? What exactly do we need to install?
So for like being able to follow along with this example, you'll need the actual like challenge file. So if you go to the Pwny CTF page, there will be like a challenge called debugger, and there'll be a file there. So you should have that file downloaded. And ideally you should also have Ghidra downloaded so that you can kind of open it up later. Yeah.
Can we download Ghidra?
Yeah, so there should be in the intro meeting slides, there should be instructions on how to do that. So if you go to the meetings page on like SIGPwny.com, there should be some instructions there. And like also, I mean, at the end of the sort of presentation here, like we can also help you get started with Ghidra. So I guess in the interest of time, I'll continue now, but yeah, if you have any questions, you can like always raise your hand or whatever. So if you try running this program right now, if you like, this is a Linux executable, if you like, either if you're on like x86 Mac or if you have WSL or something, if you run this program and give it a flag, really all it's going to tell you is that the flag is incorrect. And that's not giving you much to work with. Like it's you don't even know like what is even going on, right, when you run this program. If you wanted to figure out what flag should I give this program to make it tell me that it's correct, I essentially have nowhere to start. Like that is, you know, if you were reversing maybe a Python program, at least you have some source code to work with. You could like try looking through, you could try modifying the program, adding print statements or things like that. But this is completely opaque. So how do we reverse engineer this? Well, the first thing with, I would say, any reverse engineering project is to try to collect as much information as you can about the thing that you're reversing. So in like practical terms, in this case, one thing we might want to do is what kind of file is this program, right? Because it could be anything from like a shell script to a Python program that just doesn't have a .py extension. It could be anything really. So it's useful to know what kind of file this program is. So there's this utility on Unix called file that will tell you what kind of file it is. And if you run this utility on this program, it will tell you that, okay, this is a ELF 64-bit LSB's least significant bit executable, x86, 64, etc., etc. So the important thing to note here are ELF, which is the executable and linkable format, which is like this file format on Unix for executables, so programs that can execute, for libraries and a bunch of other things. But really the thing we want to focus on is executables. What does this file contain? Well, it contains essentially what we talked about a few slides ago. It contains the program machine code. It contains some information that the OS needs to execute this program, and it could possibly contain some symbol information. In fact, in this case, you'll notice that file utility tells us that this program is not stripped. Not stripped means that the symbols have not been removed. So we have actually some symbols to work with, and this is maybe in some sense why it's useful to kind of do this analysis before you dive into program itself. You can get some useful information like, okay, this program has symbols. And if you're more interested in this ELF format, it's like an interesting rabbit hole to go down. There's this GitHub just link that has like this diagram of how the ELF format works. There's this tool on Unix called readelf that gives you a bunch of information about ELF files. So, okay, at this point, we know this is an executable, it runs on x86. We have some symbols, what do we do now? So you're gonna take, I guess, a slight detour and talk about compilation, because how did this program end up as an executor, right? I guess before I give away the answer, does anybody want to try giving it a try? So what process resulted in, we had a C program, I guess I'll give that away, we had a C program at some point, something happened, and now it's an L file. So what happened? Yes.
Lexing, parsing, semantic analysis, then there's usually another step of semantic analysis. Then there's code, then there's basic code writing. Then opt gets run. And then you do a bunch of linker steps, and then yeah. I think I've gone on.
Yes, that's exactly correct. I mean, like you've described like what a compiler does, and the linker. But really, there is a compiler that does that does all of these steps, and then there's other stuff happening. But what the compiler does is it's going to take your source program in like C or C++ or whatever, and it's going to do some of those steps, and it's going to turn that into assembly. Assembly is yes.
Why do we take time to learn like different programming languages and then all just code it themselves?
Why do we take time to learn different programming languages if we can all code in C?
Program in assembly.
In assembly? Have you tried writing anything not trivial in assembly?
I don't know assembly, so.
So assembly is very verbose. It's very it's like a good programming language tries to help you as you try to write your program. It will give you.
Really inefficient.
It's not necessarily inefficient. It's not optimized for humans writing programs. It's essentially all it's doing is here's some instructions being executed by the CPU. And like I'm going to give them to you in some format that you can read. But if you wanted to, all you wanted to do is add two numbers, right? You're gonna have to do a bunch of stuff like load stuff into a register and store stuff back into memory. It's operating at such a low level that it's pretty impractical to try to write anything complex. And like think of it like maybe you're trying to build a house, but you have like no or maybe like IKEA kits, right? IKEA furniture kits, like they give you all kinds of nice parts and like you can assemble them. But now let's say you're doing it from like literal raw material wood and sheet metal. It's kind of the difference between doing it from like assembled kits and doing it from raw materials. And like they have done the nice steps of giving you stuff that's easier to work with. So it's possible to write it in assembly. It's not that you cannot do it, but it's going to be very time consuming, error prone. Yeah, any other questions?
Hey, Nikhil.
Yes.
I'm just gonna add to that.
Yes.
Because probably you don't need to take it, but in EC391 you have to so obviously there is a part where you just write assembly code as one of the machine problems. But also you have to deal with like context switching, because this is just one program running in one process, running in a single thread. Imagine different threads concurrently, and then you have to switch between the processes. You'll be begging for a compiler at some point.
For reference, threads are the reason that you can run multiple programs on your computer.
I write Python, that doesn't matter.
Yeah, so like in theory you could but in practice it's going to be like almost impossible for like a human brain to be able to do that. Yeah, so compiler is going to turn stuff into assembly, and then you have this thing called the assembler, which is just going to produce machine code. There's some other steps like the linker and things like that we're going to kind of gloss over because we are mostly only going to deal with programs where those aren't necessary, right? So with these steps, your original C program written in a human readable programming language has turned into this executable file. you want to know how this executable file works, so it would be really great if you could go in the other direction. Could you take this executable file and produce the source code, right? Well, that is going to involve reversing each of these steps. The first step is actually not that bad to reverse, because assembly is really, like there's a very clear mapping between assembly and machine code. Like it's it's going to be in the reference manual of whatever processor that you're using. And this is mostly straightforward and easy. So I have, like, for instance, I've got a picture here of GDB disassembling the main function. You can see some of the assembly code that corresponds to the main. And GDB was able to do the GDB is like a debugger, which we'll learn about later. But GDB was able to do this pretty easily. This is not too hard. But even this is like pretty hard to understand. Like I don't know about you, but like I don't want to reverse this by hand. Like this is not easy to do by hand. So we want to take the next step. We want to go to C code, or we want to go to source code. Right? Does anybody have any ideas? How would we do? How would we go from this assembly to human readable C programs? Yeah. Sorry, would you say that a little bit louder? Yeah, we have to use a separate piece of software. The separate piece of software is called a decompiler. The separate piece of software tries to undo the compilation process, right? And this is a hard problem. This is a very hard problem to be able to do this. So let's talk about decompilers. This is what we just saw. You have a C program, you compile it, turn it into assembly. Now we want to go the other way. So I guess open challenge for everybody. What does this piece of assembly do? And maybe could you try to figure out some sense of like what the source C program would look like? Like any ideas are great. We'll see sort of the answer on the next slide. Yeah. Yeah, so it is adding stuff. That is true. Well, here's what's going on. It's adding numbers from 1 to n. There's like a for loop in there. There's addition. There's a return. That's like all not particularly obvious to see from their assembly. So what really we want our decompiler to do is to take the assembly and then produce the picture of the C code. That's the goal. And Ghidra is a piece of software that's going to help us do that. So Ghidra is a decompiler. It's also a disassembler, and it's like this thing called a reverse engineering framework. So it does a bunch of other things. Disassembler means machine code to assembly. Decompiler is assembly to this thing that looks like C. It's not quite C. We'll talk about why later. And reverse engineering framework because it does so much more. It does, like, you can find cross references, so things like what functions call other functions, what functions refer to what pieces of data. You can do like control flow graphs, like how does the control flow in the program proceed, and so many other things. And it's written by the NSA. So it was open source a few years ago. It used to be like an internal NSA project. And it's very good. It's a very good piece of software. It's written in Java. That's why you need Java to run. It's all Java. So here's what Ghidra might give you if you're trying to use it on the piece of assembly we saw earlier. It looks very different, the like other piece of code that you see. It does the same thing, but it looks very different. The reason is that there's more than one piece of C code that can produce the same assembly. And Ghidra cannot necessarily tell which one it is. Like Ghidra is, at some level, it's a guesswork engine, right? It's going to be making everywhere a best guess of what it thinks the C code look like. But when you do compilation, like really there's information being destroyed in that process. Like it is not, in some sense, like there are completely different pieces of C code that are going to compile to the exact same thing. So it's very hard, if not impossible in some cases, to tell which piece of C code it is. So Ghidra will give you something that would correspond to the piece of assembly that you see. It may not necessarily be the original C program, and it may not be as simple as the C program. So in this case, you can see that Ghidra decided to turn our for loop into a combination of an if and do while loop. And that's in some sense something you just have to deal with, and with practice you'll sort of start seeing what these more convoluted constructs look like. And another thing, so when I learned how to do this, like this was a big point of confusion for me. The output of Ghidra is not C. It is not meant to be compiled. It is meant to be human readable. The purpose of Ghidra is to take this assembly and present it to you in some form that you can read more easily. It's not necessarily to give it to you in a form that you can throw into GCC. And then there's like research on like recompilable decompilation and stuff, but Ghidra is not that. And like we said, decompilation is the best guess. Information is lost. One of the things that you'll see a lot is that types are lost. Because like think about if you have a float versus an int, right? They both store the same amount of data. They're both 4 bytes. And there are maybe some cases where Ghidra really cannot tell the difference. So it may mistype your variable. It might just say, like you see in the example on the slide, it might give you a bunch of undefined, which means that like it's some type with that width, like undefined data. It's some variable type with an 8-byte width, but Ghidra doesn't know which one. So all is a product of the fact that it's a lot of guesswork. Another thing that you should maybe kind of look out for when you're trying to reverse stuff is that compilers will do things called optimizations. So they will take your source code and they will decide to compile it maybe in a different way than you would think for making it faster. So in this case, the source code has a string, but you look at the Ghidra decompilation and it's a bunch of numbers. And it's like Ghidra thinks this is 2 variables on the stack, one 8 bytes, one 4 bytes, and then there's like a bunch of stuff being loaded into these variables. And the optimization that's happening here is that the compiler decided it's going to be faster to load 8 bytes all at once, and then the next 4 bytes. So those 2 stacked variables that you see are really the same variable, but Ghidra cannot tell the difference. Also, question: why is the sequence of bytes backwards? Why is it in reverse? Yeah. I guess I'm looking for like 2 words. Yeah.
Like Indian.
Exactly. Little Indian. So yeah. Okay. Here's another compiler optimization. Modulo operations are very slow. Compiler people can correct me, but I think like they can take a lot of clock cycles if you have if you have like modulo by like some funny number like 30, 37 or something, it's going to be a lot of clock cycles.
It can be, yeah.
But bit masks are very fast. Bitwise AND operations are very, very fast. So a modulo 4 is the same as just taking the lower 2 bits. Like the modulo 2 is just the same as taking the lower 1 bit. So sometimes the compiler is going to take a modulo, is going to turn it into something else that's equivalent. And you can kind of.
If I remember correctly, I don't even think this type of optimization necessarily happens in the front end of the compiler. I'm pretty sure I select go ver and it just replaces it there, which is just a fancy way of saying even if you turn optimization completely off, certain compilers might just see that and be like, oh, I can directly turn this into this. So I believe that could happen. I select them.
I see. Okay. Well, right. The big picture is that the program that you see in a decompiler, which is like what actually was produced, may have some transformations being made to it to make it faster, usually. And now we will solve that challenge. So live demo. Yes, show of hands, how many of you have the challenge file downloaded? Okay, perfect. How many of you have Ghidra? Right, so why don't you get the challenge file loaded into Ghidra? So you just open Ghidra, like you go to file, there's import file, and then you can select your file and we can
If you haven't been able to set up Ghidra yet, I highly recommend sitting by someone that has and following along with them.
yeah. It should detect the language automatically. Because if you look at, like, when we ran that Linux file utility, right, the information about what language it is in the program. So it should just know that this is x86 with Linux. If it doesn't, maybe somebody can, like, help or can go and check what's going on. But yeah, I guess I'll give it a couple of minutes for people to get their, like, Ghidra debug.
Yes. You're a max. So for the back, I was like, I just calculated. Right, you just treat you there. What? Yes, yes. Oh, this is like a good one. Do that running out. When it's like, instead of multiplying this benefit, which you know, alarm combination. You also have to my exam. It's not. Doing this to yourself, not my chicken stop this. I was thinking it's fun. Getting just eating the 6 p.m. Fine, okay, fine. Oh, I have I'm so sorry, I get it. Okay, that's probably better.
Okay, so let's get started with the demo. So here's Ghidra. I have the file loaded into Ghidra. To get Ghidra to decompile this, I'm just going to double click it. And Ghidra will open this tool here that okay, I decided to open it in like a different screen. Hold up. But yeah, so it's going to open the like analysis tool.
I saw it, like look it up. It's actually a C way of building. That is connected. Check it from GitHub. There's a switch. Windows just keep down. Listen, yeah. This is the first thing we're setting. I wish I could go. That's fine. That's not a little bit alive. There's probably some process.
Ghidra just decided to hang. So
Oh, no.
yeah.
Go use IDA.
Ida,
See this assembly is a crutch. Just read the assembly.
read the assembly.
Yeah.
So true. No, IDA is money.
No, I
created.
compiler. It's just assembly.
All stuff.
And I had to go do exploit dev stuff with just IDA, not
That's
Ghidra. It's not nearly as bad as it sounds.
I mean,
No, the seed assembly really is a crutch. If you look at the control flow graph, they'll tell you more information than what the actual code does.
sure.
So if you follow the cross references, right, it's not all bad.
Interesting fact. To kill Ghidra, to kill the JVM.
Yeah.
It's very useful, especially for like DM cracker. I used all of the skill and also by like example. I'm not. She wants to divide that or graph that was like DM. When it's like a file. By CP. Oh, waited. Control flow graph is the way.
Yes, so having these
Telling you.
I'm taking post it rather than I already know from my thing. I have some just a big change.
So my Ghidra is back.
5,000.
So, yeah, so we're going to look at what's going on with this program. So we have a main function, so that's probably a good thing to look at. To decompile a function, you just click on it, and here's your decompilation. One thing that's like that may seem a little bit annoying, but that's a good idea to do is where Ghidra is confused about things like variable names, variable types. You can tell it what variable names you want it to use. You can also tell it what variable types you want it to use. So if you like set your types correctly, you can actually get Ghidra to do more work for you. So as an example, we have this like funny pointer arithmetic going on here. We know that the main function second argument is actually a like character pointer, just from like C knowledge. So if I set the variable type to character pointer, you'll see that this line is now a lot simpler and makes a lot more sense. So I guess we can just look at what yeah.
What did you rename the variable type and variable add?
I retyped it to character pointer. Because that's just like your C argv. In fact, why not rename it argv? Retype is control L, rename is L.
C programming, it might help to look at like a standard C made program, because that's usually what taking an argument is one of them.
Yeah, and sort of we know maybe from running this program that this program takes its flag as a command line argument, in particular as the second command or the first command line argument.
Yeah.
So we know that this like argv is important. So
Do you want to explain what argc and argv?
Yes.
yeah, actually a good point. So what is argc? Argc is the number of command line arguments. Argv is the actual command line arguments. The name of the program is always the first command line argument. So this argc is always going to be at least one. Let's maybe rename it to argc. And so if you look at this program, you can see that if argc is less than 2, that means you did not give it another command line argument. It says flag is so on and so forth, so that makes sense. So this is really where we want to focus. So it gives the length. So argv1 is the second command line argument, and we know that that's the flag. So let's actually let's call this maybe like flag length, right? And we see that if flag length is 0x15, which is 21, it does a bunch of stuff. If not, it just says that the flag is incorrect. So we know that our flag length must be 21. So that's a useful piece of information. Now here we have a bunch of like hex numbers being loaded into variables, and then there's this array that does, or this is for loop. Important to note, this is also 21. So maybe like each one of these corresponds to some character, and then it's doing a bunch of operations. This is actually an example of one of those optimizations we looked at earlier. So this, believe it or not, this set of variables is actually an array. It's an array of 21 characters. And this for loop is doing a bunch of manipulation on this array. So what we can actually go and do is we can go up here to where this starts, and we can sort of verify it, right? That 8 plus 8 is 16. 16 plus 4 is 20. 20 and 1 is 21. So we can let's see. So this where does it start? Starts here. So we can actually retype this array to a character array of size 21. So let's see. And sort of it might seem kind of a little bit unnecessary to do this, but the reason I'm doing this is that it really helps to have like good variable names and variable types, because when programs get complicated, like it's all going to turn into a mess. So you can pretty much ignore this part where it's loading stuff into this array. We have this for loop that looks a lot cleaner now. We have it's doing some operation on this array. And at the end of it, this is kind of the interesting thing here. So it's comparing our 21 length array with an offset of 8 to this flag and of its length 21. And if that comparison succeeds, then the flag is correct. So this is really what we're going to focus on. So in fact, when the program gets to this point, this array in fact just contains the flag because it's being compared against the flag. So one thing you could do is like reverse this by hand and like trying to figure out what's going on in this for loop. But really what's easier is to do dynamic analysis. And what happened with the projectors?
It's been happening since like my freshman year. I don't know.
Okay. So this is a place where dynamic analysis is going to be very useful because we can execute the program. We can stop the execution here and we can simply look at what's in this array. And that's just a flag, right? So how to do dynamic analysis on binaries? There's this thing called GDB, GNU debugger, that was meant for like debugging your C and C++ programs, where we can also use it for reverse engineering. So we are going to open up this file in GDB. We will stop execution here, and we will inspect what is in this variable. And that just gives us the flag. So any questions so far before we move on to GDB? Yes. Yeah, so the for loop. So the great thing about dynamic analysis is that we don't even care what's going on in the. We know that at the end of the for loop, like it's doing some manipulation on this array, right? Maybe to make it clearer, let me retype this or rename this variable to array. It's doing some manipulation on this guy. And maybe I can rename this to I. Right, it's doing some kind of manipulation here, but then at the end of this, it's comparing this array against the flag. And we don't even care what's going on in the for loop because we know that at the end of the for loop, it's going to have the flag in it. So from the dynamic analysis point of view, we can pretty much ignore the for loop. Does that answer your question? Sorry, could you say it a bit louder? How would I simplify the piece of code after the for loop? Well, I retype the argv to a character pointer that allows Ghidra to figure out that this that second argument is just indexing into one, indexing by one into that array. So that might be it. I also retyped this mess of like local variables we had into an array. Yes.
Do you like automate that or do you actually have this?
Did I automate what?
How did you write all the like?
Ghidra does that. That's the great thing, right? When you do retypes or renames, Ghidra is going to automatically handle like fixing the decompilation. Yeah, but in the interest of time, let's move on to GDB. So let's see, here's the program. So I'm going to open this up in GDB, gdb/debugger. And I have phone debug, which is like phone version of GDB. We don't need any phone debug features here. So everything that I do here is going to work in GDB. So what we want to do with GDB is we want to stop execution of this program at this point, right? After the for loop. So let's go in and let's figure out where that is. So Ghidra also gives us this this assembly here. So we see that this is at this address, and it's not important if you don't understand what this means, but this program is does not have pi, so it's like always going to be loaded at the same base address. The same address puts in GDB, even when the program is executing. Sometimes programs can be like randomized addresses, but so we are going to go into GDB. We will break at this address, so B is breakpoint. And I should, I guess, probably tell it this is X. And now we want to run the program. So run the program is just run. Unfortunately, if I just run, it's going to tell me, oh, here's the flag format, because it didn't even reach the point in the code that I was hoping for it to reach, because I saw that I didn't even give it a flag. So let's try giving it a flag. And this also fails because it's the wrong flag length. And that's kind of where the static analysis is useful. We know the flag length is 21. I could type in 21 A's. I'm going to open up Python and make it give me 21 A's. Maybe this is actually slower than just typing 21 A's. So here's 21 A's. I will run this program with these 21 A's and we hit our breakpoint. And already you can see something fun is happening here. So this is good. Where is the flag now? Well, you look at this function call. If you remember from our x86 assembly meeting, the flag is the first argument here. Well, the correct flag anyway. Your flag is the second argument, and the first argument isn't registered RDI. So we want to look at what memory is pointed to by registered RDI. Let's try to print the value of register RDI. Well, this is just a pointer. We want to dereference this pointer. One thing we could do is like do this, right? Which tries to dereference and print bytes. And this will sort of work, and maybe you can get this to work. Here's some bytes. But like you have to decode these into characters by hand. Instead, the sort of trick that I'm going to use is I'm going to pass this register into a character pointer. So then I'm going to tell GDB, oh, this register actually points to characters, and then it will very helpfully print out the flag. So yeah, that's how you would solve this challenge. Questions? Yes.
How do you get GDB?
How do you get GDB? What OS are you on? What's that? What operating system are you? Mac? You should already have GDB. No? I'm not a Mac user, so somebody who is a Mac user can answer this question. On Windows, it's probably a lot easier to use WSL. WSL is Windows subsystem for Linux. I look at the intro slides.
So I already have the high name.
You have GDB. I would think you would already have GDB if you have WSL. If you don't, you can get it from apt. It's just like sudo apt install.
Also, ironically, I think the fastest way to get access to that is actually use fastAx. If you don't want to install it on your computer. It's just a random thought, but you could. I mean,
Yes.
What do you retype the local 40 as?
Yeah, so that was an interesting point. So that was like an example of the array optimization that we saw, where it's going to take an array and like turn it into 8-point loads. So that's really an array of 21 characters. It's like a character like bracket 21.
I love guys, but it's my favorite of all times. That's
Yeah, and well, so I guess while you guys follow along with this, we have a cheat sheet for Ghidra in the slides with some useful shortcuts and things like that. So GDB, we have some info on like what GDB does. We kind of saw what it does already. Yeah.
How did you find the breakpoint?
Yes, breakpoint. I knew it was right after the for loops. I knew it was going to be and the call to like strcomp. right, that was?
Yep.
So if I click on that, the C code 9. On the like left side where it gives me the disassembly, it's going to highlight the instruction that corresponds to that.
Okay.
And then you see the address of the instruction there.
Yeah.
Yeah, and so yeah, we have this is Pwn debug, which is like GDB but Pwn. We will use this in the Pwn meeting. GDB follow along, GDB cheat sheet. And yeah, so I mean, with reverse engineering, the only way to get good at it, honestly, is to just practice. Like you can know tools, that's always useful, like know reverse engineering tools and how to use them, but really just practice. And we have a bunch of challenges on Pony CTF, starting at CrackMe 0 and going, I think, all the way through CrackMe 4, plus a few others. And like you're free to ask other people for help, like DM me on Discord or something if you that's completely fine. And I mean, reverse engineering is really a very interesting and kind of rich field. There's all kinds of stuff that you can do beyond what we looked at in this meeting. Some of this will be covered in the Rev 3 meeting and kind of beyond. And as for next meetings, this Sunday is OPSEC 1 with Min and Shagni. This is like practical security. This will be like security stuff that's useful for you like in your daily life. And next Thursday is lock picking. So if you want to learn how to pick locks, you should come to that meeting. And yeah, I think that's pretty much all we have. So thanks for listening. Here's the play, meeting play.
I'll open the line for this.
This also may or may not help with your homework.
Yeah,